So today we'll start talking a little bit more about hypothesis tests, and we'll begin application of uh, a few different types of hypothesis tests starting today. And that will continue over the next at least week or two of the course. And to that end, today we're basically brief review of some of the stuff we talked about with statistical distributions. And as a part of that, we'll go through hypothesis testing in greater detail, with the focus today being on a one sample test of means. Again, as a reminder, the term paper topics are due by the end of the day on Friday. So if you could please submit that via D2L at your earliest convenience, and then I'll plan to review those over the weekend and get you feedback, hopefully in advance of Monday's class. And then our first assignment will be due next week. I'm waiting to see whether we get through all of today's content, and if so, we should be in good shape to get that posted. And that'll basically just be a review of the things we've talked about up to this point. So the high level descriptive and summary statistics, characterizing distributions, and then a few different one sample and two sample tests using some real world data. Okay. So after today's lecture, you should be able to explain hypothesis test procedures and then apply a one sample test of means for a distribution where the variance is known. And so that, as we had talked about in the last lecture, depending upon whether we know or don't know the variance, depending upon whether samples are dependent or independent, there are different criteria that help us to determine when a specific test is applied. And so we'll detail some of that as we go through today and the following lectures as well. Okay. All right, so just a quick recap from Monday. So in hypothesis testing, the reason we conduct hypothesis tests is to allow for us to make inferences as to the underlying nature of some phenomenon of interest. And so as an example, we're often interested in measuring how a specific parameter of interest changes based upon things that we alter or other characteristics that in turn would cause variation in that variable of interest. And so as an example, we talked about speed limits and levels of travel previously, and how different types of policies might impact those specific metrics. And so generally when we do that, we would be drawing results from a sample and comparing it to some reference value that's of interest to us. So maybe we've got data on historical speeds, and we're just interested in whether or not after speed limit changes, we've seen substantive changes in those average speeds. Likewise, we talked about travel in response to COVID. And so in all these cases, we're trying to establish a series of hypotheses, collect data, use statistical tests to formally evaluate that, and then ultimately come to a conclusion and make inferences as to that underlying phenomenon it is that we are investigating. And so as a part of that, we generally establish a null hypothesis, which assumes that there's no effect of the variable or no change in the relationship between the reference value or parameter and the sample value to which we're comparing it. And the alternative hypothesis would be that there's some difference, and that difference we may have prior knowledge as to whether we would expect a greater value, a lesser value, or it may be ambiguous, and we're just trying to assess whether or not there's any change whatsoever in whatever that variable of interest would be. And so what we're going to start with today, in 2012, the state of Michigan weakened its motorcycle helmet use law. So prior to that point, Michigan was one of a number of states that had a universal helmet law. So basically anybody riding a motorcycle had to wear a USDOT approved helmet. In 2012, that law was basically scaled back so that that only applied to younger riders. So for example, those under 21 years of age, as well as those who didn't have certain minimum levels of automobile insurance, for example. And so As a consequence of that, the concern of the safety community was that weakening the helmet law would ultimately lead to higher numbers of traffic fatalities and greater societal costs as an implication of those changes. And so we're going to use some data today to basically assess whether or not there were any substantive impacts due to that change in legislation. Okay. And so just a quick recap, when we talk about hypothesis testing, it's a simple, relatively straightforward 6-step procedure. So we start out by defining null and alternative hypotheses regarding whatever our parameters of interest are that we're investigating. We establish a significance level, which will kind of dictate how we design our experiment and how much of a difference we would need to observe in order to find, a statistically significant change as it relates to the helmet law in this case. We would need to collect or obtain data from some source in consideration of how much information might be required in order for us to come to a definitive conclusion. And we'll talk a little bit more in subsequent lectures about how much data is necessary in different circumstances. And then we'd want to calculate some test statistic of interest, compare it to a critical value, and then determine whether or not we ultimately reject or fail to reject that null hypothesis and draw our conclusions accordingly. Okay. So within the context that we're talking about right now, we basically want to see what the impacts of that helmet use law were on traffic safety. And so can someone either type or unmute themselves and let me know what a reasonable hypothesis would be there? So the helmet law was weakened. What might we expect to find when we conducted an analysis of data, or even what data should we be looking at to analyze this question here? Any thoughts? So do we presume that safety is going to get better or worse or be unchanged by the weakening of the helmet law?
Probably worse.
Probably worse. You see a note here, the injuries will probably be worse. If Laura notes, there'll be an increase in fatalities among motorcycle crashes. So I think one thing to keep in mind here, going in, and we can go into a bunch of rabbit holes here, but we'll try to keep things on track here. We would expect that the change in helmet law wouldn't necessarily impact how many crashes occur. I would argue. Now, there are some counter arguments we could make there, but generally speaking, whether or not a person is wearing a helmet shouldn't have a really substantive impact on how likely they are to be crash involved. We also wouldn't necessarily presume that we'd see changes in ridership necessarily. And so if we're trying to assess effectiveness, it would probably make sense to focus on crashes that occurred, and to Babak's point here, examining how severe those crashes tend to be. Okay. Now, one way we can attempt to look at that is by basically examining how many fatal crashes or traffic fatalities occur each year as a result of those motorcycle crashes. And that's a relatively straightforward question to address with the data we have available to us. And so the way we're going to set this statistical analysis up, this hypothesis test, is we're going to operate under the assumption, our null hypothesis is that the annual number of motorcycle fatalities has not changed as a result of that change in the helmet use law. And so within the context of our parameters of interest, we're testing whether or not mu, and this would be the mean number of motorcycle fatalities in this case, after the law has changed, is equal to whatever the number of fatalities were before that had occurred. And the alternative hypothesis in this case, now obviously we could assume a one-tailed or a two-tailed. We talked a little bit about our selection criteria for those previously. In this instance, we would presume that there would be an increase here, and so we're really only interested in that one side of the distribution ultimately. And so consequently, our null and alternative hypotheses here are basically that mu is equal to mu naught, and the alternative mu greater than mu naught. Okay. And in addition to that, our next step, we need to establish what the significance level is going to be for our tests. And can anybody remind me what we mean by significance level, or what that quantity refers to? So if we say our significance level, which we denote as alpha, is equal to 0.05, what does that 0.05 mean, Lauren?
Um,
So we would have a 5% chance of doing what?
we have a 5% of making an error.
Yeah, we have a 5% chance of making a very specific type of error. And in this case, we're basically establishing how likely it is that we would reject the null when it's actually true. So if we think about that within the context of this problem, if the null is true, what does that mean in practical terms? Anybody?
Crashes didn't change before and after the helmet law changed.
Right, exactly. So if the null is true, that basically means that there hasn't been any impact on traffic fatalities in this case, and mu would be equal to mu naught. And so a type 1 error would basically be us finding that there was an impact, that fatalities did go up when in fact that wasn't true. So essentially, we just would have been unlucky in terms of how we drew that sample. So if we think about, looking at fatality data on a year-to-year basis, that's going to follow a distribution. If we've got enough years of data, we're going to presume that distribution is normally distributed. And so it might just happen that whatever the subset of data that we had sampled for our analysis is going to tell us that there's a difference when in fact there's not, okay? And we talked about this, depending upon the nature of the test that we're conducting, we can look at either a two-sided test or a one-sided test in either direction there. And so just thinking about this intuitively, these distributions are basically representative of where our test statistics lie with respect to our null hypothesis of interest. So if we assume the null is true, that difference between mu and mu naught is centered at 0, and we might just happen to sample some years of data that put us out in these tails. And we would thus claim that that data isn't representative of this distribution, and there is a difference when in fact there's not, okay? And so like I said, in this specific case, there's a 5% risk if we establish alpha of 0.05 that the helmet law change had increased fatalities when in fact it did not, okay? And so once we've established the significance level, we get back to determining which type of hypothesis test we're conducting, whether assuming a one-sided or a two-sided test, and that would largely relate to our prior knowledge and what we would expect to see as we conduct these tests. And so in this case, intuitively, we wouldn't expect to see extreme low values here. We wouldn't expect fatalities to go down. We're really only interested in the case where fatalities would go up. And so among these three different scenarios, we would focus on the second alternative hypothesis here, so mu greater than mu naught. And as a consequence of that, we would want to look at our standard normal distribution, which we'll get to in a moment here, and determine a critical value that corresponds to that significance level of 0.05, okay? Now, had we been looking at the other tail of that distribution, so maybe if we did a study and we put the helmet law back to its more stringent universal standard, we may expect in that case that fatalities would go down, in which case we would be interested in the critical value that's associated with the bottom 5% of that distribution rather than the top 5%. If we had some type of change where we didn't know whether the impact would result in an increase or a decrease, in that case, we would establish critical values on either side of that distribution. But in any of these cases, we're maintaining that same probability of us committing a type 1 error. So if it's a one tail, then alpha is equal to 0.05. we're taking the top and bottom 5% of those distributions. And in the two-sided case, we take the top 2.5% and the bottom 2.5%. So collectively, we'd have a 5% chance of making a type 1 error, okay? The case we're going to work with over the remainder of today's lecture is, again, the second one noted there. Okay, so then the next question becomes, what data could be collected and used to evaluate these hypotheses of interest? And so in this case, anytime we're interested in safety trends, Michigan maintains a database called the Michigan Traffic Crash Facts system, and that has a data query tool that we can use to easily collect data going back, I think, at least to 2004 at present. So there's quite a lot of information there. And so from looking at that, I was able to determine in the years leading up to that helmet law change, the average number of motorcycle fatalities was 106.5 per year, and the standard deviation year to year over what I believe was a 5-year period here was 9.2 fatalities per year, okay? And so those basically provide us with values for what mu naught is and what sigma is, which we're going to use for comparison purposes in the subsequent tests we're going to conduct. Now that helmet law change went into effect again in 2012. And so here we see several tables that summarize injury severity data by year among different groups of riders. And so what we're going to focus on at this point are just basically the numbers in the bottom table down here. So the total number of fatalities that occur on an annual basis are going to be of interest to us. We could break this out and look at differences between unhelmeted and helmeted riders. We could look at changes in terms of some of these other injury severity categories. So for example, maybe we'd see reductions in less severe injuries along with increases in the most severe injuries. But from our perspective, we're particularly interested in traffic fatalities. And so the data we're going to focus on over the remainder of today's lecture is what we see in the K column down here in the bottom. And just for everyone's reference, this KABCO scale, this is just indicative of how severe the injuries are resulting from these crashes. And so K means the occupant was killed, A is a severe injury, B is a minor injury. C is a possible injury, so if someone complains of pain but there's no visible injury, that would be one such example. And then O is basically no damage, no injury, just property damage to the vehicle, okay? All right, and so the way we approach this problem, I basically posited at the start that we're assuming the variance is known to us. And so on the preceding slide, we had that standard deviation value that was based upon data prior to the helmet law change. And so if we assume the variance is known to us, we can use the z-statistic. Now, in practice, the variance typically isn't going to be known to us because it's not going to be possible for us to measure the entire population. We're going to have to conduct some sampling. And so we'll talk in the next lecture about how the t-test provides an analogous alternative. But for the time being, just as a starting point to get us into hypothesis testing, we're going to assume that that variance is known and constant over time, okay? And so in looking at this test statistic, it should look very similar to a formula that you've seen previously, and that is we use the similar formula if we wanted to normalize a random variable and figure out how likely it was that we would observe a specific value or range of values based on the standard normal distribution, okay? So in this case, this test statistic is, again, distributed as standard normal. And what we're doing, we're taking the sample mean from our data set. And so in this case, that would be the fatality data following the helmet law change in 2012. We're going to compare that to a reference value. And in this case, that's going to simply be the average number of annual fatalities that were experienced prior to the helmet law change. And the sigma here is the population standard deviation. And so that's going to be known to us if we're conducting a z-test. And n is simply going to be our sample size in this case, okay? So the square root of n. And so as we look at this quantity, you may recall from last time we had introduced the term standard error. And so the standard error, as we had talked about, is basically just the standard deviation of a test statistic that's drawn from a sampling distribution. Okay, so in this case, and in any of the hypothesis tests we'll present over the next few weeks, the numerator in this equation is basically a point estimate of what the effect in this case, or the change in fatalities, was as a result of that helmet law change. The denominator here is basically giving us a measurement of the standard deviation of this, or the standard error of that top estimator there, okay? And so you'll notice this is actually just the term for standard error, the mean. And in this case, we're just basically comparing the values of a mean and subtracting off some fixed reference value here. And so consequently, it should be straightforward to understand then that this gives us an estimate of how variable the population mean is. We would get the same estimate in terms of how variable the difference in those means are compared to some reference value. Okay, so basically this isn't having any substantive impact on the test statistic here. Okay, and so if we think about this in concept, we're conducting this hypothesis test. We know that the standard normal distribution is a bell-shaped curve. And if our null hypothesis is true, that basically means what in terms of the values that Z would take? We would calculate a Z and it would be very close to what if the null is true? So if there's no impact of the helmet law change, this X bar is going to probably be very close to 106.5, and as a consequence of that, yeah, exactly. Thank you, Travis. So we would expect that we would tend to have values that are very close to 0. Okay. Now, if the null is true and that helmet law had no impact, it would be significantly less likely that we would have either very large or very small values calculated here. And so what that means is as the difference between these quantities gets particularly large, it should make sense to everyone that that's giving us more evidence that the helmet law did in fact have an impact. Okay, so as that difference between our sample mean after the helmet law gets significantly different from what that number of fatalities was before the helmet law change, that's giving us greater evidence in support of our hypothesis. In addition, if you think about the standard deviation, so this is just reflecting how much variability there are in those year-to-year fatality counts. And so as that number gets smaller, so as if we had less variability, that would also tend to give us greater confidence and a higher test statistic here. So as sigma gets smaller, our test statistic gets larger. And similarly, as our sample size increases, and we talked about this last time, the more data we have available to us, the more precise our estimates of the sample mean, or in this case, the difference between that sample mean and some population value of interest is going to be, okay? And so with that, we're going to basically apply this using the same sample data we had introduced previously. And so if we take those after period data beginning in 2012, we see that the average number of fatalities have increased to 122.67. And so subtracting off our reference value of 106.5, dividing by our standard deviation of 9.2 motorcycle fatalities per year. And in this case, we had 6 years of data. So we took 2012, 13, 14, 15, 16, and 17. Our calculated test statistic is 4.30. And you'll become more familiar with the ranges of these values as we work through the course. But by and large, that's a relatively high test statistic. Okay, so what we're going to do now, we need to compare that calculated value of 4.30 to a reference value, which would correspond to the rejection region that we're interested in for this test. Okay, and in doing so, what we're going to find, we're going to determine this threshold value, and we're going to determine this threshold value so that we have basically 5% of the distribution is at or above that calculated Z value. We would compare our calculated value to that critical value, and if it exceeds that point, what that basically means is that if our null hypothesis was true, there's a less than 5% chance we would be out in this region, okay? And so the larger our Z statistic is, the less likely that our null hypothesis is true, because we're getting further away from the 0 point that would correspond to the null being true and there being no effect in this case. And so if we're beyond this critical value, we would reject the null hypothesis and accept the alternate. And if we're not beyond that point, so if we're at any point up to, but not past this threshold, then we would fail to reject the null. Now, that doesn't necessarily mean that the Helmut law wouldn't have had an impact or hasn't had an impact. It simply means that based on the data we have available to us, we can't say with 95% confidence that there has been an impact. Okay, does that make sense? And so in this case, we should hopefully all recognize the standard normal table here. And so from the standard normal table, we basically want to select the value of Z that would occur less than or equal to 5% of the time. And so can anybody help me out and let me know what our cumulative standard normal variable value is that corresponds to the 95th percentile? So either, I guess, let me know the number or direct me where I should go on the table here to determine that. Yeah, 1.65. Thank you, Travis. So just reading across here, keep in mind these are cumulative probabilities. And basically there's two of these tables. So you're seeing the values that are greater than or equal to 0. There's a similar table that you'll see on some subsequent slides where that's less than 0. And so, 50% of our observations are going to be less than or equal to 0. And as we increase our Z statistic going down and across the table, that's encompassing a larger percentage of that cumulative distribution. And so we're just going to basically read down until we hit 95%. So we know we're between 1.6 and 1.7, and we read across until we hit the 95th percentile, and that's going to happen right between 1.64 and 1.65. Okay. And so, like I said, we're trying to find that cumulative top 5% of the distribution. It falls right between those two respective values. And so we'll go with a value of 1.645 or 1.65 in this case, okay? Now, our calculated test statistic of 4.3 is basically off the chart in this case. And so we saw a very dramatic change in motorcycle fatalities as a consequence here. And so since our calculated value of 4.3 is basically off the chart, we've obviously exceeded that critical value here. And so as a consequence of that, you'll note here that we can then reject the null hypothesis. And based on the evidence we have, it appears then that our Helmut law change did have some adverse impacts. Okay, so I guess just quick clarification here. So Farish is asking about why we're reading Z equals 1.65. So I'll try to clarify that real quickly. So these are the values that correspond to our cumulative standard normal distribution. If our null is true, we're trying to establish the threshold that would be exceeded alpha % of the time if the null is actually true. So in this case, if we calculated a Z and it was up to 1.65, there's basically a 4.95% chance we would get that extreme of a value. So our exact precise value would be halfway between these, so 1.645. For all intents and purposes, there's not a meaningful difference between those. I'm not sure though whether or not I've answered your question there or not, Farish. Yeah, so we calculated Z of 4.3. All I'm demonstrating here is how we determine the critical value to which we're comparing that 4.3. Okay. Okay, perfect. So this is our critical value, and maybe I made it less clear here. I should have put this completely off the chart, but 4.3 goes completely off this standard normal table, which, and we'll return to this point in a few minutes, means it's very, very, very unlikely. We've got a very small probability of having a number as large as 4.3. And so since we're past that critical value of 1.65, that would then lead us to reject the null. Okay. And so ultimately then the conclusion we would draw from that is that based on the data we have available, it appears that motorcyclist fatalities increased after the helmet use law was weakened. I'm probably reasonably comfortable with that conclusion based upon the data we've looked at. However, can anybody think of some potential flaws in our setup of this hypothesis test? Is there anything that may have led us to a potentially misleading conclusion here? Any thoughts? So if we wanted to criticize the way I conduct statistical analysis, here's your chance. Any thoughts? Surely there are some things that could have led us to maybe overstating what the impacts are here, or there could be some other information that would make this less clear than it appears at first glance here. Any thoughts? Okay, so the mean fatalities can change from year to year. And so Falarin, I guess you could mean several different things there. I mean, part of it just, we've got a lot of fluctuation from year to year. Now we're quantifying that fluctuation through that standard deviation term that we've included in our test statistic. A counter argument you could make, though, I guess along those lines, is that maybe the variance in fatalities is larger or smaller during the period after that helmet law change went into effect. And so, for example, if our variance was larger, that would lead us to finding a smaller test statistic, but we're just assuming that that sigma prior to the helmet law change still holds. And so I'm not sure if that's exactly where you were going there, but so that's one potential concern. What else? So if we think about just the way this was set up, we're basically just counting the number of fatal crashes that occur each year. And then we're using that metric as a basis. And so a natural question is, are there other things that could have occurred here? And so Amirali's got a good question. So if weakening the helmet law increases the total number of motorcycle riders. And so if you look at some of the lobbying that went into this law being passed ultimately, one of the arguments that was made in support of weakening the helmet law was that it would have positive tourism impact. So the argument basically is fewer people are coming to Michigan to ride motorcycles because we have a universal helmet law, and a lot of people don't want to wear helmets or be told that they have to wear helmets. And so that's one potential factor here. So if crashes are just going up overall, we're going to potentially come to a misleading conclusion here, because maybe that increase we saw in fatalities is very similar to the increases we saw in some of those other categories. So that's a good example there. Is there anything else we think might have potentially or could have played a role here? So I guess one aspect is just limitations with these data, and we've talked about that a little bit. So one thing that's missing here, and it kind of reinforces Amirali's point, is that we don't know how much motorcycle traffic occurs generally and whether any changes had occurred after that law was increased. And that's a longstanding concern. We just don't have as reliable motorcycle data as we do volume data for other vehicle types. Is there other information that would be useful or necessary? So I guess thinking about this from a big picture perspective, there are probably other things that could have made motorcycle fatalities go up. And those could be a wide range of different factors. Maybe weather was particularly bad that year. So if we had a lot of adverse rain and snow events, maybe that would have led to some changes in fatality data. Things like deer crashes. Maybe we had a very large deer population for some reason, because if you look at the fatality data, motorcyclists are particularly prone to those types of crashes. So maybe, there are some other factors that simply we don't have data to control for that would potentially play a role here. But like I said, the one big counter that's generally been brought up is either that there were more riders, and as a consequence of there being more riders, there'd be more fatalities. Now there's a counter to that. We could, instead of looking at the number of fatalities, we could look at the proportion of crashes that result in fatalities, and we'll talk about that test a little bit next week. But outside of that, I'm trying to think of other counter arguments one could potentially make to this issue. Probable change in speed limits. That's an interesting factor to bring up here. So there are other factors that have changed. Now, the speed limit increases occurred in 2017, and so that would have been captured right in the tail end of that data. So that's a great point. And if we wanted to pull this analysis forward, you have other things coming into play, like the legalization of recreational marijuana. And so all of these different factors have impacts, some of which are easy to measure and some of which are very difficult to measure. And so as we're working through and conducting analyses in this class, I want you to really think about what some of the implications are, just due to the data we have and the data that we don't have as well. And sometimes it's challenging to try to think through a few of these issues. But one quick follow-up here. Interestingly, we would have potentially seen some differences depending upon when we conducted the analysis, and that's typically going to be the case. So the more data we have available to us, generally speaking, the stronger our conclusions are going to be. And so a question that arises is, well, what if we had just done the analysis 3 years after the helmet law change? And so if we conducted the analysis after the 2014 data were finalized, just from looking at the table here, you probably noticed that the 2014 fatality count is significantly lower than the other years. And in fact, all of those crash counts virtually are lower in magnitude during that specific year. We'll return to that point in a few minutes, but just want to point that out. So if we conduct this analysis using the first 3 years of data, the primary implications here are that the mean number of fatalities is going to be less than it was as compared to our sample mean if we look at the full 6 years. And the other big change here is that instead of having a sample size of 6 years, we now have a sample size of only 3 years of data. And so we're still conducting our one sample test of means, except now our X bar has decreased down to just 114. Our standard deviation is the same as before, and our sample size is 3. And so now our calculated test statistic is very different from that 4.3 we saw previously, and now we're at 1.41. And so if we take that 1.41 value and compare it to our critical value of 1.65, we find that we do not, in this case, have a sufficient amount of evidence in order to reject. And so in this case, we failed to reject our null hypothesis. And we can't, with 95% confidence, conclude that the helmet law had an adverse impact here. However, if we were to collect some additional data, we may be able to formally reject that hypothesis. But based on the evidence we have available here, there simply isn't a strong enough evidence for us to conclude that the helmet law had an effect. Okay? But just to clarify, that doesn't mean it didn't have an effect. It just means that based on the data we have, there simply wasn't enough information to conclude that. And so the only ways we could change that conclusion is if we were to observe a larger difference, or if we were to collect some additional data. And now be careful, because that can become a slippery slope, because, well, let's just pull the analysis out to 100 years, and then even, relatively small differences would be shown to be statistically significant. And that becomes a slippery slope, and I don't want to go on a big tangent here, but just a few things to be mindful of when we think about the setup of these hypothesis tests. Okay. Now, a related term that's of importance and interest to us is what's referred to as a p-value. And so just show of hands, how many of you are familiar with the term p-value? Give me a thumbs up or raise your hand or... Okay. So Emily, do you mind giving me a quick and dirty definition of what a p-value means?
Oh no. I feel like I more raised my hand because I'm just familiar with it. Um, I'm trying to see if I could. I think you're muted.
I am muted. Sorry about that. So, okay. So p-values, and I don't want to disincentivize people from raising their hands there. So when we talk about a p-value, what that means basically is for any statistical test that we conduct, we can take the calculated value and compare it to the distribution for that underlying test statistic. So in this case, if we conduct a z-test, we can compare that calculated z-value to the underlying standard normal distribution. And the p-value basically tells us the smallest significance level at which we could reject the null. So what it basically tells us is if the null hypothesis is true, this is how likely it is that we would observe as extreme of a value as was evidenced by our sample, okay? So what this does basically, it provides us with some additional useful information that talks about the strength of the relationship we've seen in this case with respect to the helmet use law, for example. So we can actually take that p-value and compare it directly to alpha. And so as we think about our hypothesis tests, we'll reject our null hypothesis when our calculated z-statistic is greater than the critical test statistic that corresponds to alpha of 0.05. Or we can think about it as the p-value that's associated with that test statistic. If that's less than alpha, our value of 0.05 here, we would similarly reject the null in that case. So it's basically the smaller the p-value is, the greater confidence we have in there actually being a substantive effect there. And so as a consequence of that, as that p-value gets smaller and smaller, I mean, we're also minimizing the likelihood that we would have a type 1 error in essence there, right? Because if there's a 1% chance or a 0.1% chance of having that extreme of a value, that's also the probability that you would have a type 1 error in that circumstance, right? So if we return to the example that we had just worked through, so the first case, we had determined that our calculated value was 4.3, so we were off the chart there. We couldn't even measure it. We know it's less than 0.0001 in this case, and so that p-value is very, very, very small. And since that's less than 0.05, that means that we can conclusively reject the null, okay? In the second case, where we calculated our value and we were in that 1.41 range, in this case, we basically see that there's a 92.07% chance we would be less than or equal to 1.41. And so the p-value in this case is 0.0793. And so that's greater than alpha. We're not able to reject the null, but as you'll notice here, we're getting, and this kind of reinforces what we saw just comparing the test statistic to the critical value. We're reasonably close to where that 1.65 value is, but we don't have quite enough evidence such that we can reject the null, okay? So in short, with 3 years of data, we weren't able to find a difference. And with 6 years of data, we were able to show a strong difference in those numbers of fatalities. Any questions on anything up to this point? Okay. So we've talked a little bit about some of the errors that can be made when we're conducting hypothesis tests. And so there are two general types of errors that are described in the broader statistical literature, and those are referred to generally as type 1 and type 2 errors. And so these errors basically occur in certain scenarios as it relates to whether or not our null is true or not, and whether or not we reject that null or not. And so the first of these are a type 1 error, and we've already talked about this a few different times, but we'll formally refer to it as a type 1 error, is when we reject that null hypothesis H naught when in fact it's true. Okay, so in our case, if we were to find and conclude that the helmet use law changes increased fatalities when in fact that wasn't the case. And so that would basically be similar to the converse of what the data actually showed us here. So let's say if we took the 3-year snapshot and it showed us that the helmet lie had increased fatalities, but then as we increased that to 6 years, that effect went away. That would be evidence of a potential type 1 error, okay? And so we generally refer to that as alpha. And as we had talked about previously, alpha is basically fixed by us at the onset of the analysis. So we're basically establishing that we're comfortable with having a 1 in 20 chance that we would find a difference that isn't actually there, if we think about it loosely speaking, okay? In the second case, type 2 error is when we fail to reject the null hypothesis, when it actually is false. And so this would be basically what was demonstrated when we looked at the 3-year analysis using the actual data as we had presented here. So when we looked at the more robust data over 6 years, we found that helmet law had a negative impact on fatalities. But when we looked at only 3 years of data, we simply didn't have enough evidence in that case. And so that would be evidence. If we assume that our conclusion on the larger data set is correct and that the helmet law did increase fatalities, then analyzing just that 3 years of data would lead us to committing a type 2 error. And we generally refer to that type 2 error, the probability of making that error, as beta, okay? And so if we just think about this conceptually, when we're conducting hypothesis tests, there's basically 2 scenarios. Unfortunately, we never really know what the real answer is. We're trying to get at that answer through the application of probability and statistics, but the null is either true or it's not. And then based upon the data we have available and the comparison of the test statistic to the critical value, we either reject the null or we don't. And so if we reject the null, that's false, there's no error. If we fail to reject the null and it's true, there's no error. And then this is just showing us, relatively speaking, this is just kind of a quick reference table. So a type 1 error is occurring when we falsely reject the null, or we falsely, a type 2 is when we fail to reject the null when we should, okay? Now, from our perspective, generally speaking, which of these is worse from a research perspective, or which of these would we be more concerned about, committing a type 1 error or a type 2 error? Any thoughts? So in this specific case, okay, so a couple people are seeing type 2 errors, and again, I've trapped you into having to interact with me here. So Nishal, why would you be particularly concerned with a type 2 error?
2 is basically saying that we are accepting the null, even though it is false. Like we are saying there is no change in the fatalities, even though.
Now time out real quick though. I hope maybe I misstated it myself even. So we're not accepting the null, we're failing to reject the null. So that's an important clarification. We're not saying that the law has no effect, but we simply weren't able to determine that with our data. But however, I see where you're going with that. Now, from our perspective, I guess it somewhat depends upon the context in which we're looking at this question. So if we were contracted to conduct some research and we ended up committing a type 2 error, that would be a problem. So that would basically mean that, hey, there was an effect. The helmet law did make traffic safety worse, but we weren't actually able to prove that. So what are the implications of that? Well, if we think about that, it's certainly less likely that helmet law would change anytime in the near future if the preliminary data hasn't, provided sufficient evidence that there's a problem as a consequence of that. Going a step further, if Michigan found that there weren't any significant impacts on fatalities, neighboring states or advocacy organizations could use Michigan as a case study and say, hey, Michigan didn't see any increases. So those are the types of issues. Or if you're conducting the research study, and this is where it gets a little bit tricky. because there's what's referred to as publication bias, where oftentimes it would be very interesting if we find that something didn't have a significant impact. That information can be as or more valuable than illustrating that a factor did have an impact, for example. Because in this case, for example, if we conducted an extensive study and it showed that helmet laws just simply weren't effective, I mean, that's useful. Because then you think about the resources that go into helmet laws and passing legislation and enforcement of those laws and the associated costs. All those funds could be invested for other purposes, for example. Now, if you're conducting the research study, oftentimes we go into these research studies with prior expectations that we're going to see an effect in one direction or another. And if the data don't support that at the end of the day, it can be viewed from some perspective as a failure, that you haven't set out what you had proposed to do there. Now, that's a hazardous way of thinking about things, because then you're somewhat presupposing, what that difference in your data would be. And that can be a very slippery slope. And as an example, we're currently working through a phase 1 study, and we've got phase 2 funding potentially that would be available if we show good results under phase 1. And so the natural question that arises there is, well, what if you don't see good results? Because you're somewhat disincentivized in that case. You're trying to sell results that aren't necessarily there. So you just need to be really mindful of these facts. But that's something that's happens frequently. If you send out a paper for review and the conclusion of your paper is that, well, the helmet laws didn't have an impact, or this device that we were evaluating didn't have a significant impact. That information in and of itself can be meaningful, particularly if the study is well designed. Now, I mean, you could do really poor research, have a small sample with weak data, and come to a conclusion that there was no effect, and that's a different story. But for rigorous and well-designed studies, that's the risk for the type 2 errors. Now, I would argue that type 1 errors are significantly bigger problem than type 2 errors, because a type 1 error basically means that you're concluding that there's an effect or an impact of something when there actually isn't. And so if you're concluding that there's an impact, it's quite likely there'd be action taken based on those results. And so as an example, I guess we're kind of going into a circular argument here, but if we find that fatalities have gone up significantly, that's some pretty compelling evidence to potentially reinstate that helmet law. And likewise, some of those other states would similarly likely follow suit there. And so if we're basing those recommendations on flawed data or a flawed analysis, or just, unlucky circumstances, and we quote unquote found an effect that wasn't actually there, that's an even bigger problem. And it may be not quite as to the same level of severity, but as in transportation. But if we think about the vaccine development that's ongoing right now, if we were to find that a vaccine was effective when in fact it wasn't, that's a pretty severe problem. And so these type 1 errors may be somewhat more minute in a transportation context, but certainly if you're committing either of these types of errors, it's a problem. But one of the challenges is that we really don't even know whether or not these errors have occurred in many cases. So in the case of a type 1 error, we would really only know that a type 1, or in either case, really, how would we know that we've committed a type 1 or a type 2 error? Anybody? So we've done this study, we've presented our results, we've concluded that weaker helmet laws are problematic. How do we know if that conclusion is false? Any thoughts? So I guess the short answer is that we really wouldn't know that it's false until and unless we have a subsequent analysis that's, I guess, more rigorous, that would refute the findings of our own research, okay? And that's a problem. Likewise, in the case of type 2 errors, so okay, we didn't find that there was an effect. Now, a natural question there, like in this circumstance, if we collected 3 years of data, the evidence generally suggested that fatalities had gone up. However, it wasn't as large of a difference such that that was significant at 95% confidence, but had we collected that 4th year of data, that would have actually pushed us past that 1.65 value in this case. And so I guess back to my preceding point, we need to be somewhat careful with that. But if you think about it from a researcher's standpoint, we want to make sure when we conduct these studies, going in, we'd have some preliminary estimate of what would constitute a meaningful difference. And we'd want to be able to try to estimate, at least at a crude level, how much data we would need to collect in order to show that that difference is statistically significant. And so at the conclusion of that, if you're very close to rejecting the null, then you get in somewhat of a precarious situation here. Because I mean, maybe you can go out and collect slightly larger amount of data, and then maybe that shows that it's statistically significant. But you can probably see how that becomes a bit of a slippery slope there. And so ideally, we would make these decisions in advance when we're planning the research study about how much data we've collected. But in any case, just important factors to consider here. And so it might help to conceptualize this a little bit if we look at these things graphically. And so all I've plotted here are basically 2 distributions. And so these distributions, you can basically think of them as plots of that test statistic we've calculated for the one sample Z. So in the case of the null hypothesis being true, this blue distribution here basically represents actuality. That's the distribution that characterizes our fatality data after the helmet law change has gone into effect, because there wasn't any difference between the two if the null was in fact true, okay? So that's what's represented by this blue distribution. The red distribution would be indicative of an alternative hypothesis that would be based upon our sample data. Okay, so basically this is actuality if we were able to observe everything, and this is representative from the specific sample with the caveats here that this blue distribution is the null being true, and the red distribution is an alternative to that. So if this distribution holds, then this distribution is not true. We would reject the null in that case, okay? And so as we think about this, so mu1 here is basically, this is showing us where that post-Helmut law increased distribution is centered. So if we collected a whole bunch of years of data, those data would be represented by bar charts that would underlie this distribution that we see right here, okay? And so a type 1 error occurs basically anywhere in this area of the distribution for the null hypothesis, okay? So it's basically any portion of our sample data that are characterized by this red distribution that fall beyond the critical value, with the important caveat here, so the type 1 error occurs only when the null is true, okay? And so if the null is true, we're concerned with any time we fall within this alternative distribution, because we know that this alternative distribution actually isn't any different than the data that characterizes our null hypothesis, okay? And so from our perspective, the probability of a type 1 error is going to tend to get smaller and smaller as these distributions get further and further apart, okay? These distributions get further and further apart as our calculated Z statistic gets larger and larger. And so our type 1 error, the likelihood that that would actually occur is going to be a function of how large the difference in those means are. So between mu and mu naught in our case, as that difference gets larger, this alternative distribution is going to be shifted out in this direction. And as a consequence, there's going to be lesser overlap. And as it gets closer and closer, there's going to be a greater portion of that distribution. Now, keep in mind, though, this is basically this is just a set value that we're establishing to assess our level of risk here. So if our calculated value put us right here or right here, our probability of the type 1 error, we've set that at the onset is 0.05. Now our p-value, the actual probability of us observing that extreme of a value could be significantly smaller than that. But we're basically setting that alpha at the onset of that study, okay? And then when we look at the type 2 errors, those are basically going to correspond to the portions of this red distribution. So this is based on the sample data we've collected. And in order for us to reject the null when it's false, so in this case, this is the appropriate distribution that characterizes our data. This is the incorrect distribution because we've given here that our null is false. And so if we look at this distribution, we're only able to reject if we exceed this critical value, right? And so we're rejecting, if we think about this as a bar chart, all of the bars that are to the right of this threshold point are going to lead to us rejecting that null, okay? And so what that means is, if we think back to the helmet log example, if we had only 3 years of data, this distribution was centered to the left of that critical value, right? So we were centered at 1.4 as opposed to the 1.65, which would correspond to this critical value here. And so likewise, what's going to happen here is that the larger the difference in these mean values, the further this distribution is going to be shifted to the right here. And so the larger this white area is and the smaller this red area is, which would correspond to the errors that we're making over the course of that analysis, okay? So that was just kind of a brief overview of type 1 and type 2 errors. An associated term is what we refer to as statistical power. And so power is just basically 1 minus beta. So given that our null is false, and so in this case, there is a difference again between the means of those two distributions. And as a consequence of that, whatever this area is underneath the red curve and to the right of this critical value, so this entire area here is 1 minus beta, and that's just 1 minus our probability of committing that type 2 error, okay? We'll circle back to this and discuss it in a little greater detail in some of the subsequent tests here, but we can actually calculate estimates for these quantities based on the results of our hypothesis tests. We don't actually know whether or not our hypotheses are true or false, but those are basically conditional tests. So if we assume that the null is true, you know, we can establish what alpha is, and if we assume that the null is true, we could then determine what beta or 1 minus beta are. So if we assume that H naught is not true, we can make those same inferences for beta and for the power. Okay. Okay, so that got us through. I think we're in reasonably good time here. So like I said, most of the lectures won't run the full hour and a half roughly, but do we have questions on anything related to the one sample test? Because at this point, we're going to circle back on Monday and we will go through t-tests. We'll start to introduce some 2 sample tests as well. And then the homework assignment that'll be due the end of next week will basically include both those 1 sample and 2 sample tests of means, and then we'll continue building on those and introducing a few other tests as well. So term paper topic is also due on Friday, so I can certainly hang around if anybody wants to talk for the next 17-ish minutes about those topics. That would be great. Otherwise, I guess we're free to wrap up.